In this video, we are going to take a big leap forward and come up with a precise definition for the net area of a region bounded by a curve over a closed interval, right? So kind of a mouthful, but yes, as I said, it's a big step forward in our study of calculus. So what does this look like? Well, let's just do a quick reminder. So let's say you have a function. So this is y equals f of x. We have our axes there. And let's say that this is our region. And it just so happens that part of the region is above the horizontal axis and the other part below. Well, what do we know now? So I'll just let A is going to represent the net area of this region, right? So A represents the net area. And we know how to approximate this. And one method of approximation is based on these Riemann sums. So I can say that A is approximately equal to, and then I'll write down our not so efficient formula, but this is what it is for the Riemann sum, right? Here we go. So that's what we can say. Well, I mean, it's nice to have an approximation, but it would be also nice to get a handle on the exact method of or not method, but the exact value of this area or this net area, right? So in other words, how can we make this or how can we use this approximation to come up with the actual area, right? Well, in a previous video, I illustrated using a powerful piece of software that if we were, one of two things we could say. If we were to increase the number of subintervals, right, which is our n, that would in turn make delta x get very, very small. Because remember what delta x is. Delta x is b minus a over n. Well, what is a? A is this number here. It's fixed. B is this number here. It's fixed, right? So for a given function over a given interval, if this denominator gets very, very large, right? So I'll say this. So for fixed A and B, as the number of subintervals increase without bound, so it goes off to positive infinity, then just looking at this fraction, think about what it's going to be, right? A and B, let's say they're distinct, so they're different numbers. So you're going to have a positive number in the numerator, but then you're going to have a denominator that is getting larger and larger and larger. So then that fraction, so what that means is delta x will approach 0. And we saw in those plots that as the number of subintervals got bigger and bigger and bigger, it's like the actual region just got filled in. It's like, suddenly you start with just a few rectangles and you could see lots of gaps where either area that wasn't supposed to be included was included, or area that should have been included was not included. But then as n got bigger and bigger and bigger, it's like all of that got resolved. So that's going to be our definition. So we define the net, right, area of this region that I have above. So of the region above as this. So I'm going to take my approximation but make it better and better and better there are two ways I could say it. I could either take the limit of this Riemann sum as n goes to infinity, or as delta x goes to 0. So either one, I'll use the delta x, because that, thinking about it that way, leads to even more general definitions of area, which we won't really get into in this course. But the idea of making your delta infinitesimally small, very, very small, would lead to a more generalized approach, right? So we're going to say this. So in fact, I'm going to switch back to my white. So the exact area, so now that's why I'm using an equal sign, is defined as a limit, or the limit, as delta x approaches 0 of this thing. So I don't have to change any of this, right? I don't have to change any of this. I simply now have to use my limit operator to get my exact area, right? Which is, I think it's pretty remarkable, because this was done in when we defined the derivative, right? When the derivative is defined, this is just a little side note, a little reminder. And it just shows you how important this idea of a limit is, because in Calc 1 we defined the slope of the secant line. Well, it's defined in many ways, but this is one way that it can be defined, right? Let's say h is some small quantity, typically positive, doesn't have to be positive. You define that as the slope of your secant line. And then we define the slope of our tangent line as the limit of this thing. So the limit as h approaches 0 of f of x plus h minus f of x over h. Again, so we did this, to solve the tangent line problem and all the other problems that differential calculus entails. And now we're using another limit to define area, to solve to come up, with an approach, this area problem. And then we would hope that understanding the area problem would allow us to solve many other ones. And indeed, that's what we're going to see as we go through this particular course, right? So this is our definition of area. Now, is that the end of it? Well, no, it's certainly not the end. In fact, it's just the start. As again, you start with definitions. Now, this will be done in a subsequent video, but for now, this notation for the definition of area is a little cumbersome. It's a lot to write down when all you're talking about is the area of a region, right? And in a similar vein, in Calc 1, again, this was a lot to write down, when we were talking about the slope of the tangent line. So what did we do? We came up with a notation for this. Remember this notation? Your f prime, of course you remember. How could you forget, right? And so we should come up with a more efficient, maybe succinct notation for the definition of area. And this is how we're gonna define it. And then the thing that we're gonna use to denote area has a very special name. So we'll kind of talk it through a little bit, right? Okay, so we use the following notation to denote the net area of the region bounded by y equals f of x over this interval, provided this limit exists, right? So provided the above limit exists, because we know not all limits exist, right? So when we talk about the limit of something, sometimes the limit doesn't exist, and then what happens then? What happens to our definition? So we have to put this little disclaimer in. So provided the above limit exists. All right, just like how in Calc 1, when we write this down, we have to say, because remember, there are some functions that aren't differentiable. So the limit, this two-sided limit as h approaches 0 would not exist. So what is this special notation? Well, let me just kind of go through it like piece by piece. So this part, the limit along with the sigma notation, all of that becomes this little, almost like you take the letter S, like I took my little S there and just kind of stretched it, make it a little taller. You know, so it's like an elongated S. Some people call it a seahorse. But right, so that's where this goes. So the limit and the sigma notation is all wrapped up into this, right? The f of x bar k, that is replaced by basically this formula right here, f of x. So we put an f of x there. Again, you might remember this from Calc 1, that the delta, as delta gets very, very small, your difference here, or your delta, approaches the differential x. So that delta x gets replaced with dx, right? So far that's looking a lot better. But then one thing we have to convey is that we have to know, you know, because what we would like this notation to do for us is to tell us one, that we're talking about an area, and that's going to be implied by the notation. Two, that we are working with a particular function, and that's where the f of x part comes in. But we also need to know the interval. Without knowing the interval, we wouldn't have, or we wouldn't know much about its area, right? So somehow we have to convey this inequality in our notation, and what we do is this. We take the smaller x value and we put it almost like as a subscript, but kind of right at the bottom here of this symbol. And then we take the larger x and we put it on top, right? So now, and then I'm going to put my a equals, we'll put that right there. And again, the a here is representing the net area, and this is the notation that we will use, right? And this whole thing together is called a definite integral, right? So this is called a definite integral. And it has some special pieces, and I'll go through and tell you the name of each of these pieces. So let's start with the, so we know this sign, again, going back to when we did antiderivatives, we know that this is the, like, you know, you can call it the indefinite integral notation. Right, or your antiderivative, right? And A is called the lower limit of integration. So the lower limit of integration, and then by contrast, b is defined as the upper limit of integration. F of x, that's your integrand, so that's the fancy name for the function, integrand. And then finally the dx, that is your differential. Right, and again, some of these terms are familiar from earlier, in your study of calculus, and then some may be new if you've not seen a definite integral before. But this, again, is an important thing. So again, the nice analogy is what the derivative, or my definition of the derivative, is to the slope of the tangent line. Now this definition of is to the net area of one of these regions, right? So let's just look, let's just do a couple. I mean, these examples, they're not very involved. But for instance, so what happens now is, if you are given one of these definite integrals, one way to immediately kind of have a picture in your mind as to what does this stuff even mean is to picture a region. So, picture an actual function and some area associated with it. So for example, if I gave you something like this, right? So I could say that the lower limit is 0, the upper limit is 2, my integrand / function is x squared, and all of this represents the net area of some region. Well, what is that region? Well, I can sketch it because I know what the graph of y equals x squared is. And I'll just draw the relevant part of it. So y equals x squared, that's my parabola there. I'll just do that. And then I know that the region starts at x equals 0. X equals 0 is right there at the origin, so that's here. And then it stops at x equals 2. So again, I'm just going to conveniently say that this is 2. And if I wanted to, I could even indicate the corresponding y value, right? It goes up to y equals 4, because if I take 2, plug it into x squared, I'll get 4. But remember, the way this problem is defined, the region is bounded between the graph of the function and the x interval. So this right here would be the region, right? So what's nice is, just like how you can kind of visualize a derivative as a slope, you can always visualize a definite integral as an area. And then you can go the reverse, right? Because that's what a definition is. It's the if and only if type thing. So I could give you one of these and then ask you to express it using the definite integral notation, right? So I could do something like this. Give a simple function, and let's say that this is a line like y equals 3x plus 1, and then let's make it like 1 to 4, and then shade this part of it, right? Then I could say, right? I mean, and we can compute this. In fact, shortly in subsequent videos we will be looking at computing these areas exactly. But now we're just trying to get used to the concept and the notation that goes along with it. But with this region, I can express it as a definite integral. So I'll always have, in other words, these two things always have to be there. right? Those two things always have to be there. But what will change is the type of function. In this case, it's a linear function, so I'll put my 3x plus 1 there, and then lower limit of 1, upper limit of 4, right? And for certain types of areas, like this one, you know, because the function is linear, we can use geometry to figure this out. Whereas we couldn't use geometry to figure this one out because of the curved portion right there of y equals x squared, right? So we'll go ahead and stop here, but I want you to really you know, think about this concept and think about the notation. And it's not just, I mean, you will learn processes for evaluating these things, right? But many times in those processes, you forget the underlying meaning and where it came from. And that's what this video was designed to do, to say, okay, how do we go from, you know, a Riemann sum to this now definite integral, this abstract idea. So there were a few steps that we had to take for that to happen. So hopefully you formed it, you found this video informative, and I will see you in a subsequent video.